Good morning, everyone. Thank you for attending my talk on this rainy day. I'm Alaina Minarik, and I'm a double major in chemistry and cinema and media studies. And I'll be talking about the research that I've been doing as part of my chemistry honors thesis for my chemistry major. I've been doing work in the Door group, and so my title is Looked for a Magnet, Found a Potential Qubit. And I'll go into more of the technical details of what exactly this means, but I wanted to summarize sort of the process of this research, where I initially was pursuing a certain type of molecule, but then I ended up with a different and new, but still very cool molecule that I have pictured here in two different types of views, but I'll discuss that in a bit. First, I wanted to orient you all a little bit to the field of my study. So I work in an inorganic synthesis group, and that involves a lot of working with metals and synthesizing what we call coordination complexes. So this is an example of a coordination complex, cisplatin. And so the common aspects of a coordination complex include the metal center, in this case platinum, and then these molecules and or ions which coordinate to the metal, which are called the ligands, and then all of this together is called the complex. And so inorganic synthesis allows for a lot of tunability or customizability, if you will, depending on the number and type of ligands that you use. Just continuing with the cisplatin example, if you were to rearrange these ligands, then it would have very different behavior. Cisplatin is actually an important drug in cancer treatment, but if you were to change how these ligands are positioned, then it becomes toxic. So one of the things that researchers are currently interested in is using the synthetic customizability to develop single molecule magnets, which are sort of an emerging technology as our technology gets smaller and smaller. So what's special about single molecule magnets, or SMMs, is that they're different from the typical magnets that we think of, such as this bar magnet here at the bottom, and that these SMMs have to exhibit magnetic properties at the molecular level due to intrinsic molecular properties. And this is opposed to classical magnets, which derive their magnetism from interactions between the metal atoms that make them up. So single molecule magnets, such as this one, have to have some pretty special properties in order to be magnetized and stay magnetized and work as a magnet. So in the development of single molecule magnets, the periodic table is basically our building blocks. And so this group of metals here, including iron and cobalt, et cetera, is the transition metals. And this has been the focus of a lot of past inorganic research. However, more recently, researchers are taking interest in these lanthanides down here, which display distinct electronic properties and are a little bit less understood than transition metals in terms of how they bond and interact. So getting into where my research comes in, I've been building upon a motif that was previously developed by the Door group, which we call a heterobimetallic lantern complex, and that there are two metals with sort of a paddle wheel geometry. So this is synthetically variable in a variety of ways. We have the first metal, which is pretty much always platinum, but then we can also change the second metal, and then also this ligand at the end here, which is the axial ligand, as well as these ligands surrounding it, the backbone ligands. So in the past, a lot of these lanterns have been synthesized with transition metals, but two previous group members brought lanthanides into the mix when they sort of unexpectedly synthesized these interesting dimeric complexes. And just so you can see, there's one lantern, the second lantern, and then the bridging ligands. So this is a really interesting geometry with the two lanterns joined together and bridged. because it shows a lot of potential in the development of single molecule magnets and the way that the lanthanides are arranged so close to each other here and here. However, these complexes are super reactive in air and were very difficult to reproduce. So one of the goals of my project was to try to achieve a similar motif, but through a more efficient and direct synthesis, and one that would be stable in air. So in my case, I was trying to create a very similar dimer, but instead of the air-reactive ligands that the previous group members had used, I would be using chloride instead. So after a lot of trial and error, I developed a synthesis that I proposed would lead to this motif, and this gave me some small crystals. One of the cool things about chemical synthesis is that you can recrystallize the product, and then in this crystalline form, you can use X-ray diffraction to achieve a crystal structure that shows what the structure of the molecules are that make up this crystal. So this is the crystal structure that I got from my crystals. Oh, and yes, this is after a lot of effort. I ended up finding an interesting result. So the crystal structure showed that I had not achieved the dimer of 2 lanterns that I was expecting, but instead I got 4 lanterns joined together. And in addition, instead of the bridging chlorides that I was intending, I got hydroxides instead. So this isn't what I was expecting. However, it was a very exciting motif, especially since I had made it in air. And yes, eventually with some tweaks to the synthesis, I was able to make it in high yields. So this synthesis is generalizable to different lanthanides and different starting materials, which is very exciting, yielding these beautiful crystals. But sort of the main point is that these are all very relatively quick syntheses in air, and they all give high yields. And this is exciting because this motif is structurally comparable to some cutting-edge molecules that show a lot of promise in single molecule magnet development. We can see here that the lanthanides and the ligands are sort of arranged in a similar way to these existing complexes, which have been getting a lot of attention in the field of chemistry lately. So what's really interesting is that these bond distances are comparable to the interatomic distances between the lanthanides are comparable to the distances between the lanthanides and these really important complexes. However, these are very reactive in air, but mine is air stable. So the cubane geometry is not exactly ideal for single molecule magnets, because if it were a dimer, it would be a bit more linear and be more useful for that application. However, it is certainly possible to try to modify the synthesis to change the geometry and try to make a dimer instead. But the ease of synthesis and the high yields also makes this molecule really promising as a potential qubit, or a quantum bit, which is the most fundamental unit of quantum information. Which is another application of molecules that researchers have been investigating. So this Google Doodle here is sort of illustrating what a quantum bit does. Unlike a typical computer bit that stores either a 1 or 0, a quantum bit is 1 and 0 at the same time until it is observed, and then of course it's only one or the other. But so I initially thought that I was going to get a single molecule magnet, but instead I got something that could actually be really exciting in the world of quantum computing. So there are a lot of avenues that can be pursued with this initial discovery of this tetramer. We can adjust the synthesis in many ways and do reactions with it, but this is all sort of in service of bringing the lanthanides closer together, which seems to be key to developing molecules that are viable in everyday technological use. And I can talk a bit more about why if there's any questions about that. But this is just summarizing my key results, with sort of the most important takeaway being that I discovered this new molecule that is synthetically variable and is achieved in high yields and generalizable to other lanthanides and shows promise in a variety of different applications. So I'm excited to see where this goes as future group members continue to investigate what can be done with this motif. And yeah, that's pretty much it.
Time for about 1 or 2 questions, if anyone has questions in the audience.
Hi, thank you for your presentation. Could you elaborate a bit more on how qubits materially impact quantum computing? Because I didn't know that there was that link between chemistry and computer science.
So with qubits, quantum mechanics is really only observed at the microscopic level. And so qubits are molecules where we take advantage of these quantum mechanical properties to use them as sort of bits to store information, which isn't really something that you can do with bulk materials because then the quantum mechanical behavior is not observed quite so much, if that answers it.
Lovely presentation, Alaina. I just wondered if you could just share with the audience a little bit about your experience in sort of the observational sense that led you to figure out this really challenging problem, right? So what the audience doesn't know or may not know is that you didn't have a box that you could put your sample in at the end of every day that would give you an up or a down or a red light or a green light about how things were going. Mm-hmm. So just share with us sort of how that goes.
Oh yeah, so it was a lot of trial and error. So I knew that the thing with chemical synthesis is that you can't exactly see what's going on. Maybe there'll be a color change, but there's really no way to know exactly what the molecules are doing without special means of characterization. So in trying to make this molecule, I knew that it would be neutral and soluble in certain solvents that are less polar. And so when I achieved something that dissolved in a nonpolar solvent, as opposed to water, which is a very polar solvent and dissolves salts, I found that to be promising as evidence that I had achieved something that was fairly neutral and nonpolar, but I didn't know what, and then recrystallizing that, which can actually be very difficult, getting just the right solvent conditions to cause the crystals to form. The crystal structure revealed that it was actually a tetramer, which was pretty cool.